Welcome to the deep dive. So for today's deep dive, our mission is pretty laser focused. We are dissecting a paper that provides what the authors claim is the first really rigorous empirical proof that transformers perform genuine Bayesian inference.
Right.
So we're moving past all the, philosophical debate about pattern matching versus actual probabilistic computation and into something verifiable.
And that's the critical shift here.
Yeah.
I mean, for years, the central challenge in interpreting LLMs has been this identification problem.
Right.
When a model predicts the next word, is it actually calculating a true posterior, or is it just sort of recalling statistical patterns it saw in its training data?
And you can't really tell with natural language.
You can't, because there's no ground truth posterior.
Yeah.
So this paper, it solves that problem by building these very controlled, verifiable environments.
Okay, let's unpack that. This core methodology, they call them Bayesian wind tunnels. And for you listening, these are not just, simple synthetic tasks. They're defined by three really stringent technical criteria.
Exactly. 3 criteria designed to isolate this one capability. First, the analytic posterior has to be known exactly at every single step. That's your ground truth.
Your benchmark.
Your benchmark. Second, the hypothesis space has to be combinatorially massive, so big you can't possibly memorize it.
So it has to be learning an algorithm.
It has to be. And third, the task itself must demand genuine, sequential, probabilistic inference. It has to need it to work.
And the headline finding from this whole setup is what really, I think, shocked a lot of people. What did these small transformers do?
The results are just, well, they're unambiguous, these small transformers. And we're talking only 2 to 3 million parameters here.
So tiny by today's standards.
Oh, minuscule. Scrap-sized models. They achieved machine-level Bayesian consistency. They were reproducing the analytic posteriors with an accuracy of, get this, 10 to the minus 3 to 10 to the minus 4 bits.
Which is an error so small it's basically the numerical noise in the calculation itself.
Precisely. And crucially, when they ran the control group.
The MLPs.
Right. Capacity-matched multi-layer perceptrons. Same number of parameters, trained identically. They failed catastrophically by orders of magnitude.
So that's the smoking gun. It's the architecture.
It's the architecture. It establishes a clear architectural necessity for the transformer structure.
Okay, that frames the core conflict perfectly. So let's dive into the theory. Because the paper starts by formalizing why a model trained this way with standard cross-entropy should be doing Bayesian inference in the first place.
Well, the theoretical foundation is all about minimizing population cross-entropy. The framework proves that the function that minimizes this loss, the population optimum, is provably the Bayesian posterior predictive distribution.
So the math says that's the target.
That's the target. In the limit of infinite data and capacity, that is what the model should learn. But, and this is the key, the result is completely architecture agnostic. It doesn't say anything about whether a real model can get there.
So this whole experiment is about what they call the realizability question. Can a transformer, a finite architecture, actually do it? And if it can, how?
Exactly. And to test that, they built the 2 wind tunnels, each one probing a different aspect of this kind of reasoning.
Let's start with the first one, the discrete case, bijection learning.
Right. Bijection learning is a classic hypothesis elimination problem. They used a vocabulary of 20. The critical detail here is the size of the hypothesis space.
How big are we talking?
The number of possible permutations is 20 factorial, which is around 2.4 times 10 to the 18.
Okay, so non-memorizable.
Utterly non-memorizable, especially since they only train on about 100,000 samples. So as the model sees input-output pairs, the Bayes optimal posterior entropy should follow this perfect monotone staircase, shrinking by exactly 1 bit every time a hypothesis is eliminated.
And then the second task, the hidden Markov models, or HMMs, state tracking. This sounds like a much harder challenge. It's not just discrete elimination anymore.
No, this is the crucial test for recursive learning. It's sequential, it's stochastic, it requires constant recursive updates. They used 5 hidden states, 5 observation symbols. But the complexity, the real difficulty came from the diversity.
What do you mean?
For every single training sequence, the HM's parameters, the transition and emission matrices, were randomly drawn from a distribution. So the dynamics were wildly different every time. The model couldn't learn some fixed pattern.
It had to learn the general algorithm.
It had to learn to implement the forward algorithm, basically in context, using just its attention and feed-forward layers. The hypothesis space here is, it's over 10 to the 40.
So with all that complexity, how did they define success? What was the metric that proved it was really doing Bayes?
The sharpest test was all about uncertainty. The model performs correct Bayesian inference if and only if its predictive entropy, its own internal measure of uncertainty, perfectly tracks the known analytic posterior entropy at every single position.
And they measured that with mean absolute entropy error, or MAE.
Right, which gives you a direct, bit-level measurement of how correct the model's beliefs are.
Okay, let's get to the behavioral evidence then, because the results were pretty stunning. In that first task, the bijection wind tunnel, the transformer got an MAE of about 3 times 10 to the minus 3 bits.
Which is just an incredibly tight calibration. I mean, to put that number in context for you, it means the model's uncertainty is correct up to the precision of the calculation itself. And what's more, the per-sequence analysis showed it was actually performing the stepwise elimination. It was reproducing that perfect sawtooth entropy pattern.
A drop of exactly 1 bit at the right moment.
Exactly 1 bit. And the HMM results were maybe surprisingly even more precise.
Really? Even though it's a harder task.
Within the training horizon of 20 steps, yeah. The HMM transformer achieved an MAD of around 7.5 times 10 to the minus 5 bits. Just exceptional fidelity for a stochastic recursive process.
But the real test for learning a recursive algorithm like that is extrapolation. Can it go beyond what it's seen?
This is the definitive proof, for me, that it wasn't memorizing. They tested the model on sequences of length 30 and then 50. So 1.5 and 2.5 times the training length.
And what happened at that boundary? At step 20?
Nothing. The errors just increased smoothly with the position. There was no sharp discontinuity, no collapse. A model that was just memorizing would have failed catastrophically right at that boundary. This smooth degradation is really strong evidence it learned a position-independent recursive algorithm.
They also ran this elegant test on semantic invariance. Could you explain why that was so important?
Well, you want to be sure the model learned the underlying probabilistic mechanism, the belief state, and isn't just, associating outputs with arbitrary state IDs.
Like state 1 or state 2?
Exactly. So they randomly shuffled the hidden state labels. Mathematically, it's the same underlying process, just with different names. A model doing real Bayesian filtering should be completely invariant to that. Its uncertainty shouldn't change.
And it didn't.
It didn't. The MAE before and after the shuffling was almost perfectly identical. It learned the general concept of belief tracking, not just symbol manipulation.
So now we have to circle back to the control we mentioned at the start, the MLP failure. It's this contrast that really drives the point home about the architecture.
Oh, the failures were spectacular. I mean, in the bijection test, the MLP's MAE was about 1.85 bits. That's, over 600 times worse than the transformer? It showed zero evidence of hypothesis elimination. It just learned the marginals.
It was just guessing based on frequency.
Basically, yes. And for the HMM task, its MAE was about 0.4 bits, and the error was flat across all positions. That indicates a total collapse. It couldn't do the recursive belief tracking at all.
So it's not just about having enough parameters or having residual connections. It's something specific to the transformer stack.
Absolutely. The way the MLP fails shows that you need what attention provides. You need content-addressable routing, and you need compositional depth to handle these kinds of problems.
Okay, so if the architecture is the key, then how does it work? What did the internal analysis show about how the transformer actually realizes this perfect Bayesian computation?
So the authors identify this unified 3-component architecture that the transformer uses for both tasks. It's pretty elegant. First, you have the residual stream. That's the belief substrate. It's like a high-dimensional register where the posterior information builds up layer by layer.
And then the FFNs.
The feed-forward networks do the heavy lifting. They perform the actual numerical update to the posterior, and they confirm this with probes. The FFNs account for the biggest drop in error within each block.
And the third piece, attention, is the controller.
Exactly. Attention is the content-addressable routing. It figures out which parts of the belief state in the residual stream are relevant for the next update and sends them to the FFN. It's like a context-dependent memory access system.
So let's break down the geometric mechanism they found, which they describe as this 3-stage process. It starts with what they call foundational binding in layer 0.
Right. This is where the whole hypothesis space gets structured. The attention in that very first layer constructs the initial frame. And the diagnostics are really cool here. They show the key vectors at this layer form an approximate orthogonal basis over the input tokens.
So it's setting up a clean coordinate system for the whole problem.
That's a great way to put it. And they showed that if you ablate just a single one of these hypothesis frame heads in layer 0, The whole computation is just uniquely and structurally destroyed. It's indispensable.
Okay, so once that frame is set, the middle layers start the progressive elimination. This is where the real Bayesian conditioning happens, right?
Correct. And it geometrically mirrors what happens in the analytic math.
Yeah.
You see this progressive query key sharpening. As you go deeper, the attention queries align more and more strongly only with the keys that are consistent with the evidence it's seen.
So it starts by looking at everything and then it focuses in.
It focuses in. And this process is hierarchical. If you ablate a middle layer, the whole thing degrades. Each layer provides a necessary, non-interchangeable refinement step.
Which brings us to the final stage in the late layers, precision refinement. What's happening geometrically at the end of the line?
This is one of the most remarkable findings, I think. The value representations, the information actually being passed forward, they organize themselves along a smooth, one-dimensional manifold.
A one-dimensional curve in a high-dimensional space.
Exactly. And crucially, that manifold is parameterized perfectly by the posterior entropy. This geometric unfurling is how the model encodes its confidence with such high precision. It's not just tracking which hypotheses are left, but refining how certain it is.
And tying this back to the HMM task, they showed attention was critical for stability over long sequences, too.
Right, not just for the initial setup. They took a model and disabled attention only in the top 2 layers. It learned the training data just fine, but when they rolled it out to 50 steps, its error exploded.
Yeah.
It degraded by a factor of 62.
Wow.
Yeah. So that confirms attention is needed to sustain these stable recursive belief updates over time.
And this all led to a really key insight, what they call the frame precision dissociation.
Yes. What they found was that the attention maps, the routing, the structural frame of the problem, they stabilize really early in training. But the value manifold, which represents the numerical precision, that continues to get refined late into the training process.
So the network learns the structure of the problem first, and then it fine-tunes the numbers.
Exactly. Which, very satisfyingly, aligns perfectly with predictions from other theoretical work on gradient dynamics and transformers. So the empirical evidence and the theory are lining up.
This analysis just provides such an unprecedented look inside the machine. Let's try and summarize the significance here for everyone listening.
Well, what the Bayesian wind tunnels really prove is that transformers work here because their internal geometry provides the exact inductive bias needed for this kind of reasoning. Orthogonal bases, selective routing, progressive focusing. These things allow it to carve out a verifiable, low-error Bayesian manifold in its representation space.
Something a capacity-matched MLP just can't do.
It doesn't have the machinery.
The significance then can't really be overstated. These wind tunnels set a clear, verifiable lower bound for reasoning. And the results are strongly suggesting that the probabilistic behaviors we see in giant LLMs probably come from this specific architectural geometry, not just from raw scale or tons of data.
It's an architectural realization of an optimal probabilistic calculation.
Right.
So the final provocative thought to leave you with is this. We have this clear evidence now that the residual stream is the belief state. The FFNs are the numerical engine. The whole architecture implements Bayesian conditioning through geometry. So the open question, it shifts now from if they can do Bayes to how these precise verifiable mechanisms scale and, maybe how they degrade when they're applied to the messy, ambiguous, high-dimensional world of natural language where a ground truth posterior just doesn't exist.